Last period, we have studied different methods of preparation of alkyl halides. Today, we are going to study preparation methods of aryl halides. So that the first method of preparation of aryl halide, and that is from benzene to halobenzene. And these halobenzenes are chlorobenzene and bromobenzene. So by a simple electrophilic substitution reaction we can apply there for the preparation of chlorobenzene and bromobenzene. Here a benzene reacts with the chlorine in presence of either Fe or FeCl3 or anhydrous ClCl3 or a red phosphorus. The electrophile, that is H plus, can be substituted by a Cl plus. H plus can be substituted by a Cl plus. How this Cl plus forms, that is again a very important one. So there we have to study here one reaction when chlorine combines with, suppose if I take here anhydrous AlCl3, we get there a Cl plus AlCl4 minus. So here unsymmetrical breaking of a Cl to bond takes place due to presence of a Lewis acid. AlCl3 is Lewis acid because this is a having incomplete octet. So this will try to break this bond unsymmetrically to give there a Cl plus electrophile. Then H plus of benzene will be substituted by a Cl plus to form a chlorobenzene. Therefore, this reaction will be called as electrophilic substitution reaction. Now, here in a second reaction we can prepare a bromobenzene. So again, H plus will be substituted by a Br plus in presence of FeBr3 to form bromobenzene and HBr. Now, the third, again, if we go to prepare a iodobenzene in a third reaction, when benzene reacts with the iodine to form iodobenzene, we get there Hi. Now, this reaction is a reversible. First two reactions are not reversible one, but third reaction is a reversible. And why this third reaction is a reversible one, that we have to study. So Hi is a strong acid. As this is a strong reducing agent, this will provide hydrogen to this, and again I2 and benzene will form. So that iodobenzene, more amount of a yield of a iodobenzene cannot be obtained in this reaction. And how to minimize this drawback? We can carry out the same reaction in presence of HNO3 or HiO4, that is periodic acid or nitric acid. So here, what is the role of HNO3 and HiO4 in this reaction? Here, the Hi is a reducing agent, therefore its oxidation will take place. So HNO3 can oxidize this Hi into iodine. So here we will try to understand the reaction. 6Hi plus twice of HNO3 gives thrice of I2 plus twice of NO plus 4H2O. Like this way, whatever Hi will be formed in the reaction, immediately it will be oxidized into iodine. As a result, the reversible reaction will be prohibited there, and we can prepare there more amount of a iodobenzene. So here, like this way, by using HNO3 and HiO4, we can reduce this problem of a reversible reaction. Now, the another type of a method of a preparation of a aryl halides that we will try to understand, and that method is called as a Sandmeyer's reaction. Let us try to understand first the characteristic of a Sandmeyer's reaction. So that sometime multiple choice question can be asked in the examination, that what is a Sandmeyer's reaction, and 4 options will be given there. So one by one, all these 4 options we will try to understand. Here, the only one and only the answer of that is a replacement of diazonium group 2 by a chloride or bromide is only called as a Sandmeier's reaction in presence of a cuprous halides, cuprous chloride or cuprous bromide. Okay. Now once again we will repeat the characteristic of Sandmeier's reaction. What is called Sandmeier's reaction? Sandmeier's reaction is a conversion or a replacement of a diazonium group by a chloride or bromide in presence of a cuprous chloride or cuprous bromide is only called as a Sandmeier's reaction. Okay, I have written three reactions here, 1, 2 and 3. Only these two preparations are called as Sandmeier's reaction. I am not going to tell that the conversion of a diazonium chloride, benzene, diazonium chloride into iodobenzene is a Sandmeier's reaction, because here a cuprous chloride or cuprous iodide is not applied. Instead of using cuprous iodide, Ki is used here. Okay. Now here let us try to understand the diazonium, how benzene diazonium chloride is formed. Here the aniline is taken for that. Aniline. Now this aniline combines with the NaNO2 and twice of HCl So this NaNO2, sodium nitrite and hydrochloric acid will react with the aniline group, NH2 group, to form a N2 plus Cl minus, or N plus triple bond N dash Cl minus. That is called as benzene diazochloride. Diazochloride is there. Okay, minus NaCl minus twice of H2O will takes place there. Okay, now this benzene diazonium chloride, again when it react with a CuCl, in presence of a CuCl, a conversion of it will get converted into a chlorobenzene and a nitrogen gas will be given out. N2 gas will be given out there. Again, this benzene diazonium chloride when reacts with the CuBr, again we get there a bromobenzene and minus nitrogen gas will be given out there. Bromobenzene. Here chlorobenzene. Okay. Now how to prepare a iodobenzene? That again the benzene diazonium chloride when reacts with the potassium iodide, we get there iodobenzene, KCl, and again nitrogen gas will be given out there. Okay, so as we have studied here the electrophilic substitution reaction, sometime there will be multiple choice question on here the Lewis acid, that is these are the different catalysts we have used, and what is the role of a catalyst. There will be multiple choice question on that. Another multiple choice question will be there on the characteristic of a Sandmeier's reaction, so that options can be made there. Which of the following is a Sandmeier's reaction? So that sentences can be made. The first sentence can be there. Option A will be replacement of a diazonium group by a chloride or bromide. Option B will maybe wrong. B, C, D may be wrong, maybe made there wrong. A replacement of a NH2 group by a chloride or bromide. C will be there a replacement of diazonium group by chloride or bromide in presence of a cuprous chloride or bromide will be called as a Sandmeier's reaction. And the last one, a conversion of benzene diazonium chloride into iodobenzene is called as a Sandmeier's reaction. So correct option is a C1. Like this way multiple choice questions also can be asked on a Sandmeier's reaction. Okay students, now we will start a physical properties of the alkyl halides. The first one is a boiling point. First of all, let us try to understand what is a boiling point. The boiling point is it is a temperature where the vapor pressure of that given compound equals with the atmospheric pressure, as called as a boiling point. The boiling point of alkyl halide is depend upon which factors that we will try to understand first. The first one is bond polarity of a CX bond. When the bond becomes a polar one, that first of all let us try to understand. Here the bond polarity of a HH bond we can see, H2 molecule, this is a non-polar bond molecule is there, because the electronegativity of hydrogen, both hydrogen atom is 2.1 and 2.1 is there. In case of a alkyl halide, the bond polarity is, suppose here if I take a chlorine, the chlorine is more electronegative than the carbon, so dextra negative charge and dextra positive charge will acquire on a carbon atom. So therefore I can say the Cl bond is a polar bond. Now the second one is a boiling point, is another property which affects the boiling point of alkyl halide is a size of halogen atom. As we have studied in 11th standard in the periodic table, how the size varies in a group from top to bottom. If we travel from top to bottom in a group, the atomic size go on increasing. As a result, so when we travel from fluorine to chlorine, chlorine to bromine and bromine to iodine, the size of halogen atom must go on increasing there. So this size matters on a boiling point of these alkyl halides. So let us see, Rx are the moderately polar because there is a little difference in their electronegativity. Therefore, the Rx bonds are moderately polar. So again, the electronegativity of a halogen is greater than carbon atom. Therefore, the Rx bonds are a polar bonds are there. Second one is a bond strength. Let us try to understand the bond strength is inversely proportional to size of the halogen. That means how we can say, if I take a CH3F, CH3Cl, CH3Br and CH3I, so that bond length will go on increasing as the halogen size go on increasing there. Okay, so that here the bond length is in a picometer, that is a CF is a 139. In case of CH3Cl, 178 picometer. In case of a CH3Br, it is increased up to 193 picometer, and in a CH3I that is 214 picometers. Okay, so that a bond enthalpy. Okay, that relation between a bond enthalpy and a bond length, that is again inversely proportional. Shorter the bond, higher is the bond enthalpy. That bond enthalpy is measured in kilojoule per mole. The CH3F bond enthalpy is 452 Kelvin. That of CH3Cl is 351 kilojoule. In case of CH3Br, that is 293 kilojoule per mole, and in case of a CH3I, that is 234 kilojoule per mole. So what we can conclude, as the size go on increasing, the bond enthalpy go on decreasing there. Okay, the dipole moment and electronegativity. So the fluorine is the most electronegative, having a 4 unit electronegativity. So that here the dipole moment in a d bay is 1.847. The chlorine is again less electronegative compared to fluorine. So that the dipole moment must be less than fluorine, but it is little more than fluorine, that is 1.86. Then gradual decrease in dipole moment in a d bay go on decreasing gradually, but here is the difference. So that the chlorine having more dipole moment than the fluorine, or we can say the fluorine is a less dipole moment because there is a repulsion between non-bonding pp orbital electrons, because these pp non-bonding electrons are closely spaced as the size is a less one. So as we have studied, this is one property of a boiling point, depend upon bond polarity of a CX bond and size of the halogen atom. How it varies, that we will concentrate now. The boiling point of a CH3F is 194.6 Kelvin. Increases in chloride, that is 248.8. Again more in a CH3Br, that is at 276.6 Kelvin, and in case of CH3I is the highest one, that is 315.4 Kelvin. So that as we have studied, the bond polarity, as the bond polarity go on decreasing, the bond strength go on decreasing, and as the size go on increasing, boiling point go on increasing. Next property, which is depend upon a number of carbon atoms. Again, the boiling point property of a alkyl halide is depend upon how many number of carbon atoms are present in that compound. Okay, it is here a homologous series of a alkyl chloride is taken. homologous series of a alkyl chloride is taken, a CH3Cl. Here one more CH2 is added, that is ethyl chloride. One more CH2 added in this ethyl chloride, that is the N-propyl chloride. Then here N-butyl chloride is there. Okay, as there is successively a CH2 group is added, what happens? The molecular weight must go on increasing. And again, the boiling point is, as the boiling point is directly proportional to number of carbon atoms, as number of carbon atoms go on increasing, molecular weight go on increasing, as a result boiling point must go on increasing there. So how it varies, that let us concentrate. In case of CH3Cl, boiling point is 248.8 Kelvin. In case of ethyl chloride, that is 285.5 Kelvin. In case of N-propyl chloride, that is 320 Kelvin. In case of N-butyl chloride, that is 357.5 Kelvin. Okay, so as molecular weight go on increasing, a boiling point go on increasing. Second property we have studied now. The third property we will try to understand. What is the effect of branching on a boiling point of alkyl halides? So that, and a size or a surface area of that compound is how it varies, and how it is depend upon what thing. So the surface area is depend upon a branching. Here, in case of a N-butyl bromide, secondary butyl bromide and tertiary butyl bromide, a surface area go on decreasing as branching go on decreasing there. So how I can put up there the equation? The surface area or branching is inversely proportional to boiling point, or the surface area is inversely proportional to boiling point. More surface area, the surface area is directly proportional to boiling point. More surface area, more is the boiling point. Less surface area, less is the boiling point. Again, surface area is decreased, again the boiling point go on decreasing. So that again, what is the equation of van der Waals force of attraction and surface area? So the van der Waals force of attraction among the alkyl halide molecule, if that van der Waals force of attraction is more, the boiling point will be more. Again, as the size is there, as size of the N-butyl bromide is more, van der Waals force of attraction is more. So as a result, its boiling point is 375 Kelvin. As the branching increased here, instead of the Br present at N primary carbon atom, here the bromine is attached at a secondary carbon atom. As a result, the size is decreased. So therefore, surface area will be less. As a result, boiling point of a secondary butyl bromide is a 364 Kelvin. In case of a tertiary butyl bromide, the size has been decreased, surface area is decreased. As a result, the boiling point also have been decreased up to 346 Kelvin. Now next point is, we are going to study regarding the boiling point of a halogens. Now here, isomeric dichlorobenzene is taken and having a formula C6H4Cl2. There are three isomers. The first one is, in case of the first one, the two chlorine atoms are attached at a first and second carbon atom. Therefore, this is called as a orthodichlorobenzene. Now, in case of this, the chlorine atoms are attached to a first and third carbon atom. Therefore, it is called as a metadichlorobenzene. In case of this, a first and fourth carbon atom having a chlorine atom. Therefore, this is called as a paradichlorobenzene. Now, let us try to understand their variation of their boiling point. The orthodichlorobenzene having a 453 Kelvin, metadichlorobenzene having a 446 Kelvin, and paradichlorobenzene having a 448 Kelvin. Now, their melting points. The orthodichlorobenzene having 256 Kelvin, metadichlorobenzene having a 249 Kelvin, and that of paradichlorobenzene is a 323. So there should be gradual decrease, but here the paradichlorobenzene having a higher melting point, because this paradichlorobenzene having a symmetrical structure, and as a result they are closely packed. Therefore, intermolecular forces are a stronger one. As a result, it requires a higher energy to convert the solid into liquid. Therefore, the para-dichlorobenzene having a higher boiling point, melting point. Now let us try to understand the solubility of alkyl halides in a water. As the water having a high dielectric constant, in this water, the ionic compounds are soluble. Water can separate ionic compounds into cation and anion. So these cation and anions are surrounded by a water molecule. Therefore, ionic compounds are soluble in water. Let us try to understand regarding the alkyl halides. Rx bond is a moderately polar. Then Rx do not form a hydrogen bonding with the water. As a result, it is less polar. Alkyl halide cannot form a hydrogen bonding with the water. The third point we will try to understand, as this is moderately polar, Rx intermolecular attractions are a very higher one as compared to Rx and water. Therefore also, this is also the important point, as a result, this Rx or alkyl halide cannot be soluble in water. But in which compounds or in which solvent these alkyl halides and aryl halides are soluble? They are soluble in a non-polar solvent, for example acetone, benzene.